Alright, so we're gonna go over parallelism today. Starting with your do now, just going over some definitions. We talked about these definitions last week before I left, so you should be familiar with some problems and complexity. If not, take this as a review, and it's something that we need to work on. So, okay, for question number one, several problem is a decision problem for which it is possible to write an algorithm that will give a correct output for all inputs. Um, so yes, this is true. There. A decidable problem, that means it has a decision at the end. Um, it's a kind of decision problem that will always have a correct answer. That means you can decide that problem. Number two, the question is the integer even an example of an undecidable problem? So again, undecidable will be the opposite of this. Is the integer even? We know that we have ways to find if an integer is even or odd. So we have a decision for this problem. So this would be false. 3. A heuristic is best used for solving reasonable time problems. If you remember, a heuristic, it means that it's not a solution, but a good enough approximation. For complex problems, this is best. Reasonable time problems, um, they're problems that can be solved in like linear time, sublinear time, so they're not as complex. So they should have a solution, not an approximation. So heuristic, since it's an approximation, um, it wouldn't be best used for solving reasonable time problems. This is false. 4. A heuristic would be useful for solving the traveling salesman problem, which asks for a group of cities, what is the shortest route for a salesperson to visit every city and return to their home city? So this is something like going from one place to another, but notice how it says a group of cities. We know that a decision problem of can you get from somewhere to another is a decidable problem, but once you have a group of cities, it's still decidable, but the complexity explodes. It it's very complicated. So a heuristic would give you a good enough approximation of it would give you like a suggestion. There might be multiple solutions, so this would be true. 5 algorithms that run in exponential time and factorial time are said to run in reasonable time. Exponential is slow, so this would be false. Remember, reasonable time is anything below polynomial time. Algorithms running in linear, quadratic, and cubic times are types of polynomial time algorithms. Remember, polynomial is exponent. Linear is just a number, so you could think of the number as x. Oh, that's a very bad x. How do I delete this? You could think of the number as just x. Quadratic is x with the exponent 4, and cubic is x with the exponent 3, right? Like the volume, cubic feet is exponent 3. So remember that a polynomial is anything with an exponent. So this would be, these three are kinds of polynomials, so this is true. And then number 7, in the real world, the efficiency of an algorithm can make a big difference in the time it takes to solve a problem. So yes, there are times where problems are too complex, and if you have a very bad efficiency in your algorithm, it'll take super long. So these are the answers for your dinner. Let's go into the lab now. So right here on the right, I have some notes. you're welcome to take notes. So today we'll be going over um, parallelism. So make sure you have this page open. It's linked in Teams. Um, so on this page you'll learn how running multiple scripts in parallel can reduce the total time it takes to run an algorithm. So far we've worked with sequential algorithms, right? We talked about sequencing at the beginning. So when we talk about sequencing or sequential, we know that it's in order from top to bottom, at least our in our snap projects. We have a script that takes instructions from top to bottom, so you could say instruction 1, instruction 2, and so on, right? Until you reach the end of your program. That's good for our programs, but sometimes you may end up with very big blocks of code if you're trying to do complicated tasks. So we, for example, for the project that we did, the last one that we did, that was the guessing the number. We used multiple sprites to do different tasks. So our scripts were very short, and that's what this is. What this is here. We're used to seeing a bunch of scripts that all run independently, which may or may not be associated with different sprites. So we have different scripts running at the same time. So it wouldn't look like this, right? For different scripts, we have maybe we have sprite 1 here doing this block of code, and then we have sprite 2 doing this block of code, and they're different, but they achieve different tasks, right? This is kind of parallel computing. Not really, because you're doing it on the same computer, but parallel computing, it means that the program is broken into smaller steps, and they can be performed at the same time. Modern computers have multiple processors in a single computer, so you can do parallel processing on the machine on your desk. So yes, your computer takes in multiple processes at the same time, so it runs multiple programs at the same time, which is parallel computing. So you could think of that as parallel computing. Parallel computing, all it means is you can run multiple operations or programs at once. So again, going back to what we said about here of sequential, parallel would be like you have multiple programs running at the same time. Think of these arrows as instructions, so you have instruction 1, instruction 2, instruction 3. Right here you have more, and more right here, and more right here. So they all run at the same time. So answering these questions, take like 5 seconds. Read this question. How long would those sequential algorithms take to run? Select an answer and check it. Once you check it, the answer would be the total amount of these, right? So you would wait 6 seconds, then 4, then 8. So in total this would be 18. So if you got it right, perfect. If not, it would just be the total. So now this would be something similar to what we have here. You don't have this, and this is just for demonstration, so don't worry about it. We have this script, which we know is sequential. So let's click on it. Wait, let's stop and let's click on this and see what it does. So it's running, it waits 5 seconds, and then it says task 1 is done. Pretend that's like uploading a picture or something, and then you want to upload a caption with that picture. Task 2 is done. So you saw how it took 12 seconds to do 2 different tasks. Okay? So now we have this thing right here. And you might think, what does broadcast mean? So that's what we have over here. If you broadcast a signal, you can have these hat blocks right here pick up that signal. So for example, let's make a new signal and call it upload, just for that example. Like we're uploading a picture and a caption. So when this block receives upload and when this receives upload, they'll start their tasks. And you see these are the same tasks, 5 seconds for task 1, 6 seconds for task 2. So they will run. So it would be something like, and the first one we had task 1 and task 2. Again, this is sequential, but now we have a parallel. So we will have one processor doing task 1, and we'll have another one doing task 2. So notice what happens when we do this one. We wait 5 seconds, and then task 1 will be finished, and then right away task 2 is finished. Different to how this one right here took 5 seconds for task 1 to finish, and then it took another 6 seconds for task 2 to finish. So if this is 5 seconds and this is 6 seconds, in total it took us 11. Where did I put 12? My bad. 11 seconds. But for example, for this one took 5 seconds, and this one took 6 seconds. But it was, since they started at the same time, we finished in total with only 6 seconds because they started right away. Look, 1, 2, 3, 4, 5, 6. Task 1, task 2, right away. So I hope that helps you visualize how this is supposed to work. So now if you go here, how long will this parallel program take to run? This is something similar like what we did right here. So again, in parallel it took us whichever one was the biggest out of these two. So which one is the biggest out of these three? It's 8. Check your answer. Oh, it's right. I don't know why I went red. Wait. It's wrong? Oh, it would be 14. Sorry. This is just because it has a broadcast. Then this would finish, which would take 8 seconds, and then this is another extra 6 seconds. It would be the same as having like an extra something here. So this would take 7 seconds. My bad. Something else that you need to know. Okay, so we talked about parallel, which it runs multiple programs at once. That's in your computer. So now we're talking about you're supposed to know about distributed computing. This is the same as parallelism, but instead of doing different programs at once, you run, or it's a kind of parallel computing, that uses different computers. Computing, which uses different computers at the same time. So this is very useful for the internet, for apps like I don't know, like TikTok, Instagram. They don't have like a main computer that does everything. No, they have multiple computers, perhaps around the world. They have servers here, in Europe, in Australia, anywhere, and they all work together to do the same task. Um, yeah, that's what you need to know for this. Like this says right here, parallelization with the like our example is trivial, right? But for example, for Google, millions of search queries and web page edits have happened today, and it's your job to process them. If they didn't have a huge server farms with thousands of computers in each building, they wouldn't be able to keep up. So distributed computing lets you scale to very large problems. So this is very helpful for super complicated large problems where you need a lot of processes running at the same time. So let's go here. Because every computation includes a sequential portion, there's a limit of how much speed you can how much you can speed up a task by adding processors. So yes, you can add processors as much as you want, but as you saw here, there's this wait 6 seconds that will always take you 6 seconds, and you cannot speed that up. So for example, in this example, suppose the task includes a 1 minute of sequential steps and a parallelizable portion that will take an hour if done sequentially. So for this example, you have this instruction that takes 1 hour. And then you have an extra minute. I'm not going to draw that. So then, but then when you have two processes running that same one, how long would it take if you're able to split it up into two? Well, they would take 30 minutes each, right? Now, what happens if you're able to split it into three? How would you figure out how long each one takes? Well, that's pretty easy. You just divide 60 by 3. So each one would take 20 minutes. So each one of these would take 20 minutes. Now if you have, so I'll stop drawing it because it's gonna get like a little messy, but pretend that you have, so for one we know it takes 60 minutes, for two, so we'll have processors, and time. Oh. For two it takes 30, for three it takes 20, for four it'll take, so you would divide 60 by 4, that's 15. You have 15 minutes. So fill out the rest of the table or figure out how long it takes. You'll notice that by the end the difference is very minimal. So for example, here in question 4a, if you have one processor and you add one more, how much time do you save? So in this example, um, we had one processor, we're taking 60 minutes. When we have two processors, we save 30. So we saved half. When we add one more processor, um, we save 10 minutes. So we save like 1/3. Then here we save like 1/4. Um, if we were to have five 60, how much is it? So 60 divided by 5. Oh, that's 11. Oh, 12. So 12. So we only save 4 minutes. So you see how, for example, you could write it. We could write it here so you could see. We save. Right now we have 0, but here we save 30 minutes. Here we save 10 minutes. Here we save 5 minutes. And here we save 3 minutes. So notice how we're saving less and less every time. So yes, parallel computing helps us, but it's not as multiple processors or a lot of processors will kind of become useless at the end. And if you solve all the way to these, you'll realize. So for example, if you have 240 processors and you have 240 more, how much time do you save? So let's see, 60 divided by 240. So for 240 processors, let's add some dots. For 240 processors, we take 0.25 minutes. That'll be like 15 seconds. So we add 240 more. 240 plus 240 is 480. So how much does it take us? So 480. No, it's 60 divided by 480. 0.125. So it's not a huge difference. We saved, what's that? 0.25 minus 0.125. That's literally just 0.125 minutes. Not a huge difference. They're decimals. But yeah, that's called the law of diminishing returns. So click on this thing right here. The law of diminishing returns is an idea from economics that basically says after a certain point, more is not better. Exactly. So more is not better. For speed up, programmers refer to speed up of a parallel solution to describe how many times as fast as the parallel solution is compared to the sequential solution. So the speed up would just be the sequential time divided by parallel time. So for example, for sequential, this process takes us 60 minutes. So we would have the speed up for two processors. We have it in sequential it takes us 60 divided by whatever it takes us in parallel, which for a parallel of two processors it takes 30. This would be equal to 1/2. No, speed up of 2, right? 60 divided by 30 is 2. Pretty sure. 60 divided by 30. Yeah. So speed up of 2. If we try to do for speed up for, let's say, 2 processors, let's say this one is 3 processors. Now we have 60 divided by 20, because that's what it takes us right here. This would be 3. So a bigger speed up from 2 processors to 3 processors. This is important because there are times where parallel processes are crucial. For example, let's pretend that you have a bank account and I share a bank account with my brother, and we both want to take out money. So I look at the balance and I see that there's 100, but at the same time, my brother looks at the balance and he also sees that there's 100. So he sees that there are 40 available, um, and then he takes it out. So now the new balance is 60. So now there's only 60 because he took out 40. But now, at the same time, I requested 20. So would the computer adjust the balance to 60 or to 80? So that's why parallel computing is very important. And it's very hard to achieve parallel computing because you have to account for all of these tasks going at the same time, and if they affect one another, it can be complicated to program those things. Because because the second ATM changed the account balance after ATM1 looked at the balance, ATM1 didn't know that the balance had to be changed. So yes, since my brother took away the money since he took the money away after I looked at the balance, then I didn't know that he had taken that money. And since this one adjusted the balance, that means I have now $80 when I'm supposed to only have 60. An extra 20 bucks. So imagine if this happened. Infinite money glitch. So think of some benefits, challenges like you saw there, right? It's very hard to really program a computer to take into account all those things. That's why parallelism is one of the hardest things to take into account. If you try to code here with multiple sprites where they're all based in from one signal, that will be very complicated. So just a little self-check. What is the speed up for this parallel solution when compared to the sequential solution? So again, the speed up is the sequential divided by the parallel. So let's see how long these take, and let's solve it. So we have this sequential solution that takes 6 plus 4, that's 10, plus 8, that's 18. So we have 18. And then for this one, we have the 6 seconds that are not parallel, so these are always there. And then the longest one out of these two, which is 8. 8 plus 16 is 14. So that's our answer. So that's it for this lesson. Make sure you answer the exit ticket here based on the notes you took, if you took any notes. And if not, you have this one here. So sequential, parallel is multiple programs one by one. Distributed computing, multiple computers at the same time. The speed up is how faster it became. And processor, use that by process of elimination. Let me know if you have any questions. You can comment or reach out to me any way you can. And we're done. Thank you.